our last speaker of this session is Artem Prykhodko from Shevchenko National University of Kyiv, and the title is Size Effects and Surface States in Spin-1 Semimetals.
Hello, dear colleagues. Thank you for the possibility to speak today. My name is Artem Prykhodko, and I will tell you about my latest research, finite size effects and surface states into the spin-1 semimetals. And to the introduction, triple-fold fermions are defined as fermions whose energy dispersion has this linear cone and a flat band intersecting at the touching point of two cones. There are several ways three bands can touch in a point. All of them could be called triple-fold semimetals, triple-fold points. But as I understand the situation, the name actually spin-1 fermion is kind of an oxymoron, but it is not. I think it is not a official term. It's like a conventional jargon. So the ones which have this this dispersion are called pseudo-spin-1 fermions, and they can be described by these Hamiltonians. That's where they have their name. They are this Hamiltonian is a linear combination of SO3 generators. Yes, to describe, to investigate the finite size effects and the surface of this material, we need to somehow, one of the ways to do it is to model the abrupt surface between the semi-metal and, for example, gapped material, vacuum or insulator, and to model the gap material, we would like to open an energy gap. It can be done via the constant mass term, and we will show that any perturbation, any constant perturbation, cannot open an energy gap. So any perturbation can be expanded in the Taylor series, and the series term of the Taylor series is constant. So it is the most important one, and well, from topological point of view, it is it kind of can be obvious that the energy gap shouldn't be opened by the constant term, because we know that these materials are topologically protected. These points are topologically protected, but we can show it directly. For example, Weyl fermions, it is obvious from the starting point, because we understand that the only matrix that doesn't that isn't added to the only Hermitian matrix that isn't added to the initial Hamiltonian there is the energy translation. Here it is not that obvious, and we add the most general constant Hermitian term to our Hamiltonian. The only thing that isn't added here is the purely imaginary part, because it will only give the translation in the K space. So if we take the determinant of this sum of the initial Hamiltonian plus the mass gap, mass term, the determinant of this sum is the same as we took the characteristic equation for this sum and equated the energy to zero. And if we show that for any set of constants alpha, beta, gamma, and mu's, there is some real k that satisfies this equation, that will mean that for any mass term at zero energy, there is a solution. And if it is at zero energy, if there is a solution at zero energy for any mass term, then the mass term, I will show it again. As you can see, mu1, mu2, and mu3 are linearly independent. And this way, our mass gap also contains energy translation. So if there is no mass gap at the zero energy, there won't be any mass gap at any energy. Oh, mass gap, energy gap, I'm sorry. So we can rewrite the equation 3 this way. So the not, or maybe obvious thing is that here is determinant. It will completely define our proof. As we can rewrite the equation 4 as equation 6 via some orthogonal transformation. So from the equation 6, for example, you substitute lambda 1, lambda 2, lambda 3 are all positive, then it is some ellipse of rotation, ellipsoid of rotation, and there are solutions. If you substitute one of them negative, then it is obvious that there is solution. If you substitute, for example, two of them are negative, again, it is obvious that there is a solution because, for example, if lambda 2, lambda 3 are negative, here we have a negative number. Okay, we take kz equals 0, and we can get here a negative number. And if one of them is 0, if one of these lambdas is 0, then it's obvious that substituting any k, for example, if lambda 3 is 0, any kx will satisfy this equation. So no mass gap can, no mass term can open the energy gap. Okay, and also we will investigate six-fold fermions. They are present in the same materials, cobalt silicate and rhodium silicate, but at air point. So the additional, like how it differs from our threefold fermions is only the fact that they have oh my god, how it's called? They are doubly degenerate. Okay. Yeah, and the mass term here is obvious. Oh, that's one mass term. It doesn't mean that there are no others, but we investigated this one. So from topological arguments, we know that Bell nodes always come in pairs. So and we based on Okugawa Murakami paper proposed, they proposed a simple model for Weyl fermions, so they come in pairs. And we use the same idea to make it for spin-1 fermions. Then it is easy to open a mass gap, an energy gap. But we need, if we just substitute instead of m small, m big, minus m big, minus m capital, then we will have electron hole symmetry. So we need to break this symmetry. So at the zero energy, we will have energy gap. So naive matching of all components, despite our Hamiltonian is linear, and we would expect that matching of wave function will be a good boundary condition, is impossible for any state, for bulk state or for edge, for surface state. It can be shown explicitly. We won't do that because there is nothing interesting in those calculations. But for any set of energy and in plane momenta, it cannot be done. So the correct approach is matching only two out of three components, and we will show why. First argument can be kind of obvious is that the current component perpendicular to the interface must be continuous. And for it to be continuous, as you see, psi2 must not be continuous. It does no limitations on that component. So, and why that discontinuity has arisen? It is because we omitted quadratic correction, which gives only quantitative difference for linear bands, but qualitative difference for flat band, because now our flat band gives additional freedom, additional degree of freedom to our solution. It has additional arbitrary constants in the general solution. And furthermore, if we look at states of now weakly dispersive band, which with non-zero delta is weakly dispersive, with zero delta it is flat, which corresponds to our energy, non-zero energy, we see that these states go to the same very component that is discontinuous. If we take the limit, delta goes to zero. So it explains why this component is discontinuous, because we lost additional states which did made it continuous. So using new boundary conditions and our Hamiltonians, we can calculate Fermi arcs. Here you can see at these pictures that the green regions represent the projections of bulk states on the surface, and blue curves correspond to bottom surface, and red curves correspond to top surface. Top surface means that the semi-metal is below, like y below zero, and vacuum is above zero. Okay. What we see here is for the same magnitude of energy, but different signs of energy, the curves differ. That's because we broke the electron-hole symmetry. So for the six-fold fermions, we also needed our new boundary condition. We need to match only 4 out of 6 components. We obtain this dispersion relation, which if we simplify it, making the mass gap infinite, energy gap infinite, it must be of order of work function, so it must be big in comparison with energies we are investigating. We have this dispersion relation for the surface states. And now to finite size effects, we need to consider this system that we can call it thin film, or brick, but infinite into dimensions. Yeah, it is of thickness L. So solving for triple fold semimetals gives us this difficult dispersion relation without discussing it, because it will take a lot of time. We'll jump to looking the plots which we obtain, and we see that for finite size are Fermi arcs. They become not discontinuous, but they do not always touch the bulk, the projection of bulk states. Here's for top pictures, they represent energy 0.2 gamma m, and bottom pictures 0.6 gamma m. So also you can see localization of states, and mostly, as you see, even for thin films, the surface states are localized on the top or on the bottom surface. There are mostly no parts of these arcs where they are not red or blue.
You have 5 minutes left.
Okay, that must suffice. So yeah, we can quantitatively describe those curves. There are two regions, main regions, and one additional region in between them. So yeah, these are the regions of energy where the arcs behave differently. As you can see, the leftist picture below and above. So from this we can see that Fermi arcs between in the region Kz from -1 to 1, they have two intersections, top and bottom, and for energies above gamma mu over 2, there are no intersections, and the evolution is as so. First, these small parts of Fermi arcs, we call them petal-like curves, they for smaller energy, they first disappear, and then the central loop disappears. Here the evolution goes as first we see that curves touch each other. After that, the petal-like curves are created, and then they also disappear. There are two critical thicknesses which describe when at which thicknesses these qualitative changes appear. So critical thickness first describes when the petal-like curves disappear, and second critical length describes different scenes for different energies. For small energies, it describes when central loop disappears, and for energies above gamma m over 2, it describes when in this region two curves touch. The third region is from 0.43 gamma m to 0.5 gamma m. It is when first central, it looks like this picture, but first disappears central loop, and then petal-like curves disappear. Again, we solve the problem, but for six-fold semimetals. We obtain this dispersion relation, and from the dispersion relation, and also from the dispersion relation which we solve for bulk states, we obtain these plots. What we can see, which can be of interest. So the energy gap, which is for bulk states, is obvious. This P over 2 divided by L, multiplied by Fermi. Yeah, and what is for bulk for surface states? We see that the one branch but doubly degenerate divides into two, and one of these two is has a gap, energy gap. So this energy gap, we were interested why they behave differently. So we
Then please proceed to the conclusion if you
that's
if you want to have questions.
That's the final thing, the final slide. I think the conclusions just repeat the whole picture. So we can look at the internal structure of wave function. We can define the part that is localized on the top and on the bottom surface. We can they relate via this equation, and so the gapped branch is the sum of top and bottom functions, and the gapless is their difference. It is understandable why it is sum. If you look again, you see that the gapped curve, the gapped branch is continued into bulk region.
No.
Yeah, and we calculated approximately the density of states for 6-fold semimetals. Okay, I think I'll just proceed to questions.
Okay, so let's send the speaker. Please, questions.
Thank you for your talk. My question is rather naive. So still, maybe intuitively, could you give us a reason why those systems are called spin-1 fermions?
Yeah, as I said, that's because of the mathematical model that is used for them. As we see, this Hamiltonian can be described as a vector product of vector k and vector of matrices, which are spin-1 matrices.
Okay.
Yeah.
So can you go over one of the pictures where you show the Fermi arcs? Yeah, so for instance, this one. So I'm used to Fermi arcs being closed, or even the up and the down, they connect to the nodes.
There is unusual
Exactly.
Fermi arc which extend into infinity, which means that they go through the whole Brillouin zone. Such Fermi arcs were obtained in numeric calculations, not by us, but by other researchers. As I understand, these are the feature of spin-1 fermions.
So my question would be, where do we end? The Brillouin zone is not infinitely large, right? So
Yeah. So they go through, as I understand, they go through the the boundary of Brillouin zone, and they imagine like it has gone through the boundary of the Brillouin zone, it has reappeared and closed.
but then it reappears on the other surface. That does not make sense.
There is a periodic like the surfaces of the brilliant zone are periodically connected.
Is it brilliant zone or it's flat? Is it the brilliant zone or it is flat?
On the pictures?
Yeah.
No, it is just
We
don't know how the brilliant zone looks from the KP model.
Just continue on.
Okay. There is,
Yeah, actually, okay, I could ask about this, let's say, flat part. How actually the spin naively, yeah, I would expect that you have this spin-1 you could construct from different states. So you have here how many states for each K you have here. It is degenerate state, or these are three states, or these are four states, or
these states. So in sense of quantum mechanics, they can be called degenerate because they all have the same energy. Again, it is approximately the same energy because we omitted the quadratic term. But from the point of view of condensed matter, we call degenerate states degenerate when they have the same energy and the same wave vector. And all of these states have different wave vector.
yeah, I mean here you have let's say for certain K you have one state, you have three states, yeah? Or
Yeah.
three, not four, so it is three states.
Yeah.
If there are three states, how it could be one spin-1 if it should be 1.5 as maximum, is it? If you have three states, you have three fermions, real fermions, and is it possible?
Why 1.5? What is the argument?
The spin-1 fermion is living at this node. That's the idea, where you have the degeneracy. Whatever you want to call it.
okay, are questions online? Okay, then if not, let's send the speaker.